So hopefully you can see my screen at the moment. Perhaps you can. Yep, fantastic. Okay, so I'll get started. So this project started as a sort of a tool to kind of look at different ways of delivering content. And realistically, my focus at the very beginning was to use virtual reality. And I'll give you a little bit more detail about that as we go forwards. This was all done before lockdown started. So again, this was designed to be in class and collaborative and sort of change the way that students are able to interact with content. Although obviously following lockdown, following the blended learning format that we're likely to follow going forwards, I think this provides a new opportunity to get students to engage with content and perhaps see things in a way that otherwise they wouldn't have the opportunity to do so. So just to give you an overview of what virtual reality and augmented reality are, virtual reality is essentially this really immersive experience where you have the virtual reality headset. It covers your vision completely, and you're able to create this really unique learning or this really unique environment. And so you have ultimate flexibility of what you put into that environment in terms of the content, and also the limitation of that is actually the computing power of the devices that you happen to be using. So quite commonly, you can see here with the virtual reality headset, it's not uncommon that it would be rigged up to quite a powerful computer that would be able to render all of these complex 3D images and dynamically change them as you move through the environment. So it's completely immersive. One of the limitations of this actually is the fact that potentially it's too immersive. So where you have individuals who are moving in an environment or the environment is moving but they're not specifically, that can make people feel quite nauseous. So that's really a key limitation of that technology. Now, we actually started off using this for the project. However, we later switched to augmented reality. And I don't know if you've seen examples of this, but there was quite a popular app a couple of years ago, the Pokemon Go app, where you have digital content that's rendered over the real world environment. And so in Pokemon Go, you had people running around public parks trying to find Pokemon and capture them using their phones. And it was created quite a frenzy, and it was designed to get people up and moving. And at the time this was released, I was in Pittsburgh, and a lot of the students had taken to riding the bus network to actually get around having to walk anywhere to use the app. So it did work to some extent. More recently, you might have seen the augmented reality gig that was actually run by EE. I think it was a Bastille gig at a London station, and you have all this additional content that's actually rendered in real time, and it just kind of adds to the experience. The key aspect of this is that what you can have is you can have multiple people viewing the same object at the same time on different devices. And not only that, that each person using that device gets a different perspective of that same object. So there are some really powerful opportunities, I think, for collaboration using this technology. Now, in the case of both of the examples that I've shown you here, this is based on geolocation, as in there's a physical location in the world where this content will be triggered and will be available to you, and you'll be able to see it. The alternative to that is by using a trigger image, and this is what we did, because obviously, even though we knew we would be at the university, it wouldn't be clear which room we'd be based in. So having these trigger images that would activate the digital content was sort of the way forwards for this. So when we started off looking at VR, we actually got access to a couple of Oculus Quest headsets. And the advantage of using these is that I mentioned about the sort of, you need a powerful computer to be able to run this content. All of the computing power is within the headset, which is a really powerful thing to be able to do. So you can go to any teaching classroom on campus, as long as you've got your headset, you can turn it on and off you go. And the idea of this was really to introduce the collaboration through having someone who was going to lead during a session, and you'd have other students who could provide guidance to the person who's wearing the headset, additional information. Of course, this relied on being able to essentially cast the experience to other monitors in the classroom, so such as the whiteboard. So you can have one person who's immersed in the experience, and then other people who are also able to witness what the person with the headset is also seeing. One of the initial things we tried with this was actually to take a model of a cell, and this was obtained from Sketchfab, and I'll touch on Sketchfab in a little bit more detail later on. But it's a great resource for various models. And what we did is we blew up this cell to the point where a student could actually walk through it and actually see the content and then explore it and look at the different organelles of the cell. And it was a really sort of quite immersive and unusual experience, and an interesting way to sort of present the basics of cell biology. But one of the limitations we had was the university network wouldn't actually allow us to cast, which really kind of limited what we were able to do with the technology. And ultimately, this made it a solitary experience, which is not what we wanted from this technology. So we switched to AR. Probably the most challenging part of this was actually trying to find the most suitable software. I previously actually used software called Aurasma. Unfortunately, Aurasma was later retired and then acquired by HP. Is now HP Reveal, and I don't know if the software is still available beyond sort of commercial and marketing purposes. But we did also look at other alternatives such as Google AR and VR, and also the software packages offered by Unity. There was one additional software package that sort of came up, and this was the one we went with in the end. It was ZapWorks. And the advantage of using ZapWorks is that firstly, it had a nice app, the Zapper app, literally, that uses the camera on your phone or tablet device, and it scans the content in any way that the other apps do, but it will also render the digital content. But critically, it also contains, or it encompasses, an editor, essentially a studio environment where you can create this digital content and map it. So here I'm showing you one of the models that we actually used. We made a copy of GFP and made it into a model and highlighted aspects of the model that we thought were interesting. So how you get the fluorescence from this three-dimensional protein structure. And you can see here this disk at the bottom that essentially represents the trigger image. And so you can see we can render this three-dimensional object relative to that trigger image. Ultimately, the way that we did this is by taking the structures from the Protein Data Bank, which is a fantastic resource for three-dimensional structures and all sorts of additional information. In order to get these into any functional or useful form, you have to open them in PyMol and just save them as an OBJ file. And that converts it from being a series of coordinates to a three-dimensional model, essentially. And then the model itself can you can add animations to it or add color, which we did. One of the things I would highlight for you is that if exporting things and converting file types is not your thing, Sketchfab is really a fantastic resource for that. So as of January this year, there's 300,000 free downloadable models. Not all of them are science related. In fact, the majority are probably games and sci-fi and everything else, but it does include quite a substantial selection on physiology models, things like muscle contraction, the heart, and also molecular details. I think there are quite a few models of the coronavirus at the minute. So really worth checking this out. One of the reasons I bring it up is that ZapWorks actually has a button that will just allow you to import these models directly from Sketchfab. So it's a really useful tool. There's no conversion of files involved. You can go and literally search in here, search for the model you want and import it. And then add the trigger image, and then you're ready to go with the content. The last thing to mention with ZapWorks is that there are a really good set of resources for video tutorials on how to use the software and how to get it going. I've probably watched about 3 or 4 of these. They're about 10 minutes long before I was able to get the content up and running as just a basic setup. So here's what we actually did. We ran a small study. So we created 4 different models based on several proteins that we thought kind of encompassed what the learning outcomes that we wanted to achieve from those sessions. So, for example, proteins with multiple subunits, various secondary structures, obviously a mixture of tertiary and quaternary structures, fibrous versus globular proteins, and also an example of a protein with pathogenic potential. So here we've got amyloid beta, so the misfolding of this protein leading to aggregation and the formation of these fibrils. So again, these encompassed sort of a different array of the concepts that we wanted students to take away from the session. And Laura Reeves did a fantastic job on this. She was an MSc student who just graduated, and she rendered all of the colors on these models as well as adding the text. And in the case of GFP, she added the sort of additional details and the animations. It wasn't animations as such, that's what we want to go on to do next. And again, she optimized the size of the model. So this is something that is a bit more trial and error. You've got obviously the size of the trigger image will dictate the size of the model that's rendered. And you want to make sure that the tablet that you're using or the phone that you're using is capable of visualizing the whole model when it's being scanned. So what we did in the session, we had 4 tables set up, and each of which was set up with a model on each of the tables. We actually used iPads in this example, and the reason being, we thought, well, firstly, they're available. Secondly, they've got a larger screen size. And thirdly, it takes away the variation in terms of accessibility that students might have if they don't have a particularly up-to-date device, or they've got different screen sizes, or all of the variation that would sort of come along with that. And again, you can see how these images are then rendered in real time in 3 dimensions. And again, because we took all the chairs away from the session, the students were able to walk around these models and see them. And then where you've got multiple students visualizing the same molecule, they're getting different views of the same molecule. So you can see here a student is zooming in on the fluorescent components of the protein, whereas this person's sort of looking at the broad beta-barreled structure of GFP. So again, there's a lot of opportunity for collaboration here. So in terms of the way that we actually ran the session, we wanted to test whether there was an advantage to students to actually run sessions like this, whether there was any benefit to it. And so we took 20 students that were enrolled on a biochemistry module, and we split them into 2 groups, so 2 groups of 10. In the first group, they sat what was a formative test, which comprised 13 questions. There were 15 marks available, and they had 15 minutes to do it, so nothing too substantial. At the end of that, they would go and do the AR session, and they would then complete a survey at the end. Whereas the second group would do the same bit in reverse. So they would start with the AR session, and then they would complete the formative test, so that both groups would have equal opportunity to complete all of the activities available, but only group 2 would have the benefit of having done the AR session before they do the formative test. We also included a kind of a control group, and this was made up of individuals from our Learning Technologies office who they are not enrolled on, or they're not studying biochemistry, they don't come from a biochemistry background, they haven't sat through my lecture, lucky for them, and they also hadn't participated in the AR session. So we kind of used them as a control for the guessability of the test that I essentially administered. So when we did that, you could see the control group here. Again, this just gives us an indication of the baseline guessability of the test. Scores are shown in percentages. Group 1, we saw a shift upwards. And with group 2, the group 2 were the ones that did the AR session before the formative test, and we saw a very mild increase. It was a very subtle variation. And again, one of the things we learned from this is really we need more substantial testing, and possibly to run this with a larger number of students to really tease out what's going on here. I did give the students the opportunity, because they weren't given the answers immediately following the test, they were given the option to come back 4 weeks later and actually resit that test. And again, we saw a sustained level of performance. So all by one person, they didn't do any worse. So this was kind of promising. Potentially there's something in there, but I think it needs further investigation, really. What was a little bit more indicative is the students' responses to surveys. And during the survey, they were actually given 3 Likert-style questions and 3 free text answers. And so for the Likert-style questions, I asked them whether they thought the AR helped their understanding of the content covered. Um, and thank you to the speaker a couple of weeks ago who introduced the Likert package, really fantastic, and it really does only take 2 lines of code to get it to work. But you can see here, 80% of the students responded agree or strongly agree to that statement. I also asked them whether they found the AR content more engaging than the lecture alone. And again, 89% responded with agreement to that. And it also asked them whether they would want to use AR in class in future, in terms of whether they would like to continue this sort of style of session. And actually 90% of them said they would like to do that. So I thought that was quite promising. In terms of their actual responses to the use of AR, ask them for their general thoughts. So without prompting them either to say anything positive or negative. Most of the responses actually suggested that they found it useful and it helped them to understand. Some of the key comments that I got from that said it was much easier to see the structures as a 3D model, which makes it easier to visualize and understand. The second point, I think here, a little bit more critical. It is a beneficial addition to learning content, but I don't think it should be focused on too much unless it is relevant. And I think that's a really important point to take away. Unless there's something specifically to be gained from the visualization of these models and trying to get students to develop their deeper understanding or apply their understanding, I don't think we should be using it for the sake of using it. And again, I struggle to understand this topic as it's not stuff you can see, but this definitely helped to a certain extent. I did actually ask them then for what they thought the positives of AR would be. And again, this just sort of reiterated, well, it brings the proteins to life and it's interactive, which is great. It's what we wanted to achieve. I also prompted them to suggest any negatives of the technology. And again, what sort of came out, one example was sometimes it loses connection, but maybe due to Wi-Fi. I think this is more to do with the logistical issues of having the trigger image being scanned by the camera on the iPad. So it has to be held within certain proximity to it. And I think if you deviate too much, or if you're viewing the trigger image from an extreme angle, it doesn't pick it up particularly well. Someone here suggesting not sure learning as much depth. Again, I think that's an important point to consider. This is designed to be an aid, but it's not going to replace our lectures and the core content that is associated with that. And also space might be an issue in a larger class. So really just the takeaway points from this is that AR software and the models, they're actually surprisingly accessible. There are 2 links here, and I sent a 1-page how-to guide to Nigel, which I think will be made available shortly after. There's a series of links available on there that give you each of these and guide you on how to actually create some of this content. But ultimately, you can use AR to create engaging and interactive content. And the overall impact of the technology on academic performance really requires a little bit more investigation. However, I think it looks promising. So in terms of where we're going next with this technology, again, I want to rerun this with more students and to measure this with a more comprehensive test. This might be a little bit more ambitious given the move to blended learning environments. And again, to look at whether it actually helps with the sort of higher levels of thinking. So I tried to touch on this in the test that I gave them by showing them a picture of, for example, a histone and the crystal structure of a histone with the DNA wrapped around it, and ask them, well, how many times does the DNA wrap around the histone? Which is something that if you were looking at a 2D crystal structure of that, it can be quite challenging to pick that out. But whether your ability to imagine these things in 3 dimensions is helped in any way by the activities that you've seen before would be something of interest. The other thing I would like to do is actually build this with dynamic models, and I mentioned this earlier in terms of incorporating animations. I've included Art of the Cell by John Liebler from Harvard, his animations of kinesin. It'd be lovely if we can have these motor proteins working in real time in front of the students, especially for things like sarcomeres, and muscle fibers and things like that, to see what's actually going on at the sort of molecular level. Lastly, it's really now to switch this to the VLE so that this can be delivered online. And actually, I've sort of made an example of this, which I'll show you now. And the idea is to introduce the students to some information that they can read through, to try and get them to download the app and visualize the content as they would, and then also to make notes and try to answer specific questions about the content. Now, importantly, the realization that not all students are going to have access to tablets and phones that are going to be capable of doing this. I think it's important to build in sort of a fail-safe. So if you don't have a phone or tablet, what you can do is you can embed the models as three-dimensional objects using Sketchfab. So this is something that is now actually available. You can go and download these models, the ones that we've created, and I'll make sure they're available to the community. But again, this is a nice way just to make sure that all of the content is available to all of the students. And this is as simple as just creating an embed file. So the same way that you would embed a YouTube video onto your Sol page or onto your VLE, rather. And so with that, I'll hand back to Nigel.
That's brilliant. Thank you very much. That's a really nice talk and lots of things to think about there. We've had some questions that have come through on the chat as you've been talking. So we'll go through them in chronological order. VR is definitely a motion sickness issue for me. With the augmented reality, how much data do systems gather about the students? I.e., is there potential for accidental gathering of information about location, etc.? Do you know?
That's definitely something to look into. I don't think it goes far beyond if it's location, it'll be their IP address. You don't have to sign up to the app. There's no login details that are required to get access to the content. So other than IP addresses, which would be registered otherwise at the university, no. But it's definitely something to look into.
Okay. The models look fantastic in 2D, and he's sure they're better in AR, but wondering about the resources and time to make each model and how much access is needed for the students to access the model in terms of resources, how you'll continue with that working remotely, which I think you kind of answered a little bit towards the end in terms of embedding in VLE. But what's the sort of like the time constraints in terms of making these?
I think once we had sort of a pipeline for how these models needed to be altered, it really is. I mean, the first one took a good couple of hours to sort out, and in terms of rendering colors and all the rest of it, it's certainly a lot quicker when you're doing this second or third time round. I suspect it's somewhat close to about half an hour. But this is where you're taking a model that has no color or any interactive features or anything associated with it. It is just physically a three-dimensional model. What you can do is, if you're using Sketchfab, the time taken, it would take me about 10 minutes really to do that, and that's generous. I mean, you would literally import from Sketchfab with one of the models that we've already created. There are plenty more on Sketchfab itself, which you as the educator would be able to decide which is appropriate for your course. But as you assign the trigger image, and then away you go.
Okay. What do you theorize the differences in learning might be for students between using an AU app to view a 3D protein versus actually giving the students access to a 3D model, e.g. a 3D printing or sculpture? You got any thoughts on that?
For me, it's actually the prospect of being able to include animations and additional information. We kind of touched on this with one of the models we had, where we started to embed things like the number of amino acids in the peptide that make GFP. I think the fact that you can hide additional information in those models is a sort of an attractive thing to be able to get students engaging with this. I mean, if you had a 3D model, yes, great, you can move it, you can look around. but actually that's the limit of it. If you have digital content, you can have things that you're going to click. There are models where you can click on mitochondria and it'll bring up additional information or links to further resources. Really, there's a lot of scope there for additional learning.
David's just put in, I just costed 200 lysozyme models that cost £800 from an external printer. This would be cheaper.
Yeah. Blimey. I will say, actually, of all the options we actually looked at, ZapWorks, I managed to, I ran most of this study off a trial license, and we actually bought a license, and it's for an academic, it's I think it's either £300 or $300. But either way, it's a lot cheaper than a lot of the software we actually looked at.
And a question from David as well is, have you looked at how this application links to object-based learning theory, which I know is one of his?
I haven't, but I will definitely do that.
You got collaboration there, David.
Yeah, it is my hobby horse. Not hobby horse, my hobby is object-based learning. So yeah, it's well cool.
Fantastic, thank you.
I do have one question. I've always struggled to get PyMol to work on a Mac. I don't know whether you've actually had any experience with that, because you used iPads and things like that for the actual rendering, but did you use a Mac or anything for the actual creation?
Yeah, so I have a Mac, and to be honest, the controls that are required to operate PyMol are challenging, to say the least. In terms of all the buttons that are required just to rotate a molecule, I'll be honest, it's with the Studio the Studio for ZapWorks, it is so much easier. It is, you've got the option to move the molecule up, down, left, right, rotate it, and all the conventional things. It is a lot easier than using PyMol. I mean, I've used PyMol to map mutations and variations and make predictions on about particular mutations. This is far easier, and it works on a Mac as well.
Okay, brilliant. We've got a question from Isabel as well. If it only takes around 10 minutes to colour the 3D molecule, can you use the principles of this technology and ask the students to colour some relevant parts of the molecule themselves as a learning exercise?
Yes. So sorry, the colouring of the molecule probably takes a little bit longer, but I do really like the idea of bringing the students in and getting them to create their own molecules and their own three-dimensional objects. I've seen some nice research on the advantages of getting students to create the content and take ownership over it, and then present it to others as content they've created. And I think there's a real advantage to doing that.
Great. And David's asked whether he can ask you a question out loud. So I'll hand over to David.
Yeah, sorry, it would have taken me ages to type it all out. One of the principles about object-based learning theory is the communication aspect that it brings about. So it's not actually the object in its own right that's the learning gain. It's the fact that it's an opportunity for the students to talk to each other. So my question is, whilst you were delivering prior to the formative test, did the students interact with each other whilst holding the iPad? So were they like, oh, wow, look at this. I can turn it around. I can see this thing. Oh, have you seen that part? Absolutely. And it's that helped them understand it rather than the actual object itself. That's
absolutely. It was the dialogic learning. It's the continually question each other and sort of saying, have you seen this? There was a fantastic moment in this session, and unfortunately we didn't quite capture it on camera, but there was a part where basically everyone had sort of clustered around one of those tables, and of course each of them's holding an iPad. There's about 10 people clustered around a table, and what they didn't realize is that if you physically take the trigger image and you rotate it, the image rotates for everyone. So someone had asked the question, how do you know there are 328 amino acids in GFP, or in this particular variant of GFP? And so I put my hand down on the table, rotated the entire image, and everyone around the table goes, oh, as they realize that actually the entire models, they're all looking at something slightly different. And so, there's this great opportunity to get them sort of saying, well, actually, have you seen this? In terms of if there was information hidden in there, particularly, they'll talk to each other, and I make sure, did you see all the information that was available?